first half, we showed how we did it using matrices, and we managed to do that using the express version rather than the prime version. Here we are today with the prime version. Let's see if we can do something different. So we take that panel, and instead of using arrays, we're going to be using combo boxes. So instead of alpha being equal to that degrees, we will put in input, output, basic combo box. So we've got start at 0 and units in this case are degree. Add some more, which you do by clicking on the matrix and you put a few more under. So we'll do column 5, 10, 15, 20. Scroll down a bit. And another one underneath. 25. So these are the references you're using, but here's the actual value. In this case, we're using the same thing. And again, 20. So now a combo box. So now we don't need the val authorized. We just have a regular, straightforward equation. Easy. So the roof length, just the width by the cosine of the angle. And again, we have our wind load on the building, and we turn that into a combo box. So what do we want to do? So let's have something that we will call wind. And we will assign that a combo box. So so input basic combo box. And the labels we will give it below. And we'll give 32. Now, there might be something special about that. You'll see why in a minute. So matrices, insert below 1, 2, 3, 4, 5. So you have low, medium, high, very high. And then we have extra high. We don't have a 4. Right, so we have 37, 44, 50, and 55. We want another column, so insert on the right. 0.61, 0.82, 1.16, 0.50, 1.82. And we can get rid of the final row. We might want to put in something else, like a label. And in a format. So we insert to your right. That's now text. Oops. So the text values can have spaces in, but the variable values can't. Okay. And it might say, what on earth is that figure you've put in? So I'm going to borrow that for a moment, and I'm going to define a unit. We'll do it over here. So ms is equal to one of those things, a meter per second. And we'll define that using a variable to turn it into a unit. Okay, so I want that one highlighted. Oh, that one highlighted. So now get rid of that. It doesn't know what vSit is. So we want to know what vSite is. So we can type in from the pull-down box, and we take the value from there, and it's going to be 0. So now we have 55 meters per second. And we also want to know what PZ is, so we can turn that. And that is also equal to wind, and we give it the second value, which is actually indexed as 1, because our origin starts at 0, which is mightily confusing. And so from our combo box, let's have the grid on. Let's have major grid lines. Let's line things up. To line things up, you can do a select, and you can move things with your arrow keys. So our wind speed, explain that. If you're using the latest version of Mathcad Prime, when you type a space in, it turns a variable into a text string. And we'll look at wind pressure. To PZ. So if I change that from extra high to high, you get a different value for vSite PZ. Again, and back again. So I don't need any of that. Let's go back to this. Our wind pressure coefficients are the same. Now we should have added those into there. So what we'll do is we'll edit that, put in another column. So use the matrices, add a column to the right. And so the pressure coefficient is minus 0.9, minus 0.9, and minus 0.9 for roof degrees 10 degrees or less, then go to 0.7. Minus 0.4 and minus 0.3. So those are the suction coefficients. Okay, so now it's confused it because you've got two variables in there. So now with angle, you need to tell it which one. So it's going to be the first one. So pick that as 0. And does it follow through? Yes, pick that as 0. There's all sorts of knock-on cascades there. So now our PU that have been defined as an array is defined as alpha, and then we're going to pick the array, and it's going to be the second one, which is indexed as 1. So my roof pitch of 25, if I change my roof pitch to 10, I'm back up to minus 0.9. Okay, simple so far. So the wind loading on the top half of the walls, let's make that statement a bit smaller. And W comes out as 3.3. And we've got our wind loading on the top of the walls. Wind uplift. Assuming a simply supported span as minus 5.14. So some of the things over here I can get rid of because I don't need those anymore. Need those anymore. Roll down. So the lateral wind is now going to be H times PZ, which gives me 3.3, and CPU times RL, It's going to be minus 5.14 kilonewtons per meter. Okay, so there's the diagram of our roof on plan, and we want, yeah, this is another cute thing it does. It turns it into an array. We'll delete that for the moment because we don't need it. We don't need that. So the shear on the walls of V, just multiply, let's say WL over 2. The bending moment in the roof panel, WL squared upon 2. Okay. And we'll put that back up. So you divide the moment by the width of the building, you get a tension force of 12.36. Now we've said that our fixing spacing is 250 millimeters. This shear on the fixing in the short wall due to the roof diaphragm action is simply the spacing of the fixings multiplied by the shear. Then you divide that, I don't want to multiply it, and divide it by the length of the roof, and we get 0.81. Okay, now we're looking at the shear in the fixings on the long wall due to the diaphragm action. We're looking at parallel action now. So VL, we've got simply the tension force divided by half of the length multiplied by the spacing of the fixings. So the shear there is a mere 0.412 kilonewtons. Shear on the fixings in the long wall due to the loading on the wall is simply the loading on the wall multiplied by the fixing spacing, because the load is given in kilonewtons per meter anyway. The vector sum, get rid of that. So what's it equal? It's equal to 920 newtons, or 0.9 kilonewtons. Vector sum there. How does that compare with VDES? It's a little bit bigger, so it exceeds, as we thought before, tension on the fixings in the long wall due to wind uplift, minus 1.29. Okay, now to the connection design. Very much as before, but now we're going to compare it with the applied load, VDES 2. And we're going to divide that by the capacity, which is the VB. And we're going to get the 0.65. What does that mean? I'll let it express them in percentage. Give it a percent, knock down the decimal places. So our UR1 is equal to 65%. I want to color that. Okay. So we're good with that one. Now we're looking at pull out and pull over. UR2 is now equal to the TDES divided by pi. Okay, so now we've got TDES. Let's turn that into percentage again. And knock down the decimal places. Don't like it as expressed as a minus, so let's put an hours in front of that. ABS. Okay, we've got 54%. That's fine. Okay, let's go to screw connections. So what we want, combined shear pullover. So UR2 squared plus UR1 squared, and then we UR3 will take the square root of 2 It's 85%. Now you're allowed to go up to 1.1. Let's reduce the decimals and give it a nice color. Okay, now looking at the aluminium skins, same as before, and now we've got to compare the applied load divided by the capacity. So we're looking at V dash 2. There you go. In tension, you're looking at pull over force. Oh, let's just copy that, paste that down. And sort of V dash, you're looking at T dash. We want the amps. And looking at P nov. 4%. So we'll take out the timber wall plate. So that's the simply supported span. And again, our screw diameter is 6.3 millimeters, which is 14 gauge. Get rid of that. We have our QNV and shear. So we now want U4. Yeah, UR4 is equal to V as 2 divided by the capacity. So just copy that, paste that in there, and go equals. Turn that into a decimal, not a decimal. Turn it into a percentage. Knock down the decimal places, and it looks like we're okay with that. Looking at the withdrawal from the timber in tension, our screw penetration is 35 millimeters as before. So our QKT is 2.7, and that works out as our design strength of the joint in tension as 1.948. So now our utilization ratio 5. The absolute value of T dash divided by QNT. That gives us, let's have a look at what we have. We've got the max UR1, UR2, UR3, UR4, UR5, with less than 1. So it's okay. So we have an if statement there. Just no, it tells it's no good. And that's the end of it. Or is it? So that was for a typical screw, but what else could you vary? Now the next bit is to select the different screw. Okay, so we've now got a different set of values, and we can pick. So we've already had this prepared earlier, and we have basically a table, and we can pick as many as we like from 10 through to 14, and this gives us the other values that we will need. So instead of DF is 6.3, let's get rid of that. Get rid of that. Now DF is 6.3. The TPI isn't really that important to us at the moment, so put it to one side. It's again using the combo block of the matrix, and you're selecting QKV there. Now 1, so I can get rid of that. Give that to that. So the KT1 and the KT that. So instead of that value, Put that one in, bit of that in, and you should get the same number. Aha, big deal, you say. If I change it to 12, everything changes, like magic. Put that in there. Okay, and there we have it. Just tidy it up.